Hello, I'm Mr. Herman. I'm making some videos for my class, but who knows, maybe one day you'll see this too. This is for Math 30-2, and let me tell you a little bit about the idea with these videos first. The idea is to streamline the content as much as possible in these notes so that the majority of the class time can be spent practicing and applying our skills. So these notes are pretty example focused so that we can go through ideas, see them in action all at once, and then get on with it. They require that you, the student, are writing a lot of things down on the notes, and they're kind of like check-ins every so often just to make sure you're following along. And they're just simply awful if you use them as their only resource. These need to be in conjunction with a lot of practice work, with a lot of using the textbook, or if, who knows, this goes to you and you're not in my class, then hopefully you have notes from your own teacher. So there's a strategy behind what these notes are for. With that being said, I'm going to make 3 videos, I think, maybe more. Will depend how miserable functions are. But I'm going to make one for my unit, logical reasoning. In this unit, we include a discussion on set theory, including mostly the basics, again, like I said, and then just a nod of the head towards logic puzzles. Um, in logic puzzles, generally, I think most teachers will spend some time maybe doing a research project on this as well. Hint, hint, nudge, nudge, what's coming up. Um, but it's something to me that I kind of feel like if we're spending so much time throughout the year preparing for the diploma, logic puzzles is more of a do than a teach. And so I'm not going to have a lot of notes on that. We're just going to look at some examples. Set theory, though, it's like learning a new language a little bit. And so you really got to know the words that I'm saying so that we can actually communicate as we go on. Without further ado, we're going to go on. And like I said, lots of terminology, lots of nomenclature in this one, little dense, but then so are you. So enjoy the video. So when we talk about set theory, we're talking about collections of numbers or objects. And actually, we're going to use an even better word here. When we talk about what is in a set, oh, wow. Sorry, my computer is lagging there. No, I just suck at drawing lines. Okay, anyways, we're going to use this word, an element. Element. Okay, elements in a set. That is what we're talking about when we talk about what is in a set. So a set is like a collection of ideas or objects, or since we're in math, usually numbers. And these objects we call elements. So a set is a collection of elements. Let's see if I remember how to make this work. I do. Great. It's been a while since I made one of these. So let's look at some sets as ideas here. And we'll, like we said, do it with numbers. So what we're going to do is we're going to create a set that is defined by this sentence. Natural numbers less than or equal to 20. And so the natural kind of inclination here is let's write all those numbers out. So I will do that. And I'm just going to let you awkwardly watch this while I do it. This is really fun. It's early in the morning on a Sunday, so I guess I'm not a very good conversationalist right now. I'm just super focused on not missing anything because if I do, it's going to be really embarrassing. Okay, so here are all the natural numbers less than or equal to 20. Something that might be really important for you before this unit is review what the types of numbers are. So you've got natural numbers, whole numbers, integers, rational numbers, and irrational numbers. And I don't know if you don't learn math in Alberta, maybe you do talk about complex and imaginary numbers, but we don't. So there you go. Natural numbers, I can count to them. So starting at 1 all the way up through 20, I've listed all the numbers I can count to. This is the set of natural numbers less than or equal to 20. Now, when I talk about sets, I have to notate this in a certain way. So first off, a set is going to have a name. When we talk about a set in this example, all of the numbers we're going to use in this example are what we call the universal set. That's all of the elements that will be used in any of the sets throughout our example. And so to give it a name, I'm just going to call it U for universal. And then I'll tell you what it's equal to. I can't just leave it like this because this is kind of nonsense notation. what I need to do is I need to denote to say that it's a set by using these winged brackets. Okay, that's actually one of the best winged brackets I'm going to make. So set your sights low. Those are pretty good. These wing brackets are kind of like the container for the set, right? So I'll say set U, which again, remember I said this is our universal set. Let me write that really quick. I think my penmanship's actually getting better on this, which really tells you where the bar was beforehand. So anyways, U, our universal set, includes is equal to this box of numbers, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So that's our set, U. Um, this is pretty nasty, right? So maybe we'll write it another way. One way you can write a set is you can actually just say it descriptively, right? So I could say the set U is all natural numbers. That's an M. Let's try again. Numbers less than or equal to 20. And this is kind of a little easier to do. Ooh, nice bracket. But it's not that much better, and it's kind of it feels a little not very mathematical. So not a huge fan of this, but it gets our point across. What we really want is we want a way that we can denote this set in a meaningful, helpful way. And so we're going to use what's called set builder notation. Now, if you've been in Math 20-2, which you need to have been, it's a prerequisite, you've seen set builder notation when we describe the domain or range of a function. And so this isn't anything new, but this is kind of what it was designed to do. It's designed to take this collection of garbage here and truncate it, make it into a smaller, more manageable collection. So here's how I can do that. I'm going to say that the set U is equal to, and we'll say elements X. So it's X such that X is less than or equal to 20. And then because a lot of numbers are less than or equal to 20, I can have negatives. I have to include the idea that X is an element of our natural number family. Okay. That N I'm drawing there is just kind of my way of showing that. Some people just put an N, but like a lot of math texts will have like an N that looks a little fancier. There it is. I just draw two lines and then do the N. Um, element of, you might want to note this down. This symbol means element of, that means it belongs to a certain group or set. So in this case, any of the numbers in our set U must also belong to the set of natural numbers. That's numbers you can count to. This statement hopefully makes sense. X is less than or equal to 20. This is like a grade 9 inequality. And then finally, this symbol here means such that. And it's like saying, I'm going to say X is my elements, and they are such that this is true. Okay. So this is set builder notation. Uh, And actually, this has a name too. This list of numbers is called roster notation. Um, roster is sometimes the only way you can do it, right? Like maybe you're listing elements that aren't numbers, they're just names of people. And you can't say X such that names have to rhyme with Braden. Although that might actually get you a pretty big set. That's kind of our setup here, right? We've got one more thing we're going to do before we go, though. And sometimes I'm not so much interested in what is in the set. I might actually more care about how big the set is. And so if I need to note how large a set is or how many elements are in a set, I can use this notation. The number of elements in the set U is equal to, in this case, 20. So number of elements in a set is equal to 20. If you count the numbers from 1 to 20, you count 20 numbers. Who would have guessed? All right, so that's kind of our introduction here. Now let's see some more cases here. All right, even natural numbers less than or equal to 20. You can write these numbers down if you want, but I'm going to save some time. I'm going to just move right into our set builder notation. And so I'm going to give the set a name. We're going to call it E. Ooh, okay, good enough. And remember, I've got my wing brackets. Okay. It kind of looks like the profile of a face. There you go. That is not better. Okay, one last try. There you go. That one's pretty good. So I'm going to call this, let E include the elements 2x. Why 2x? Remember, this is like the definition of an even number. Even numbers must be divisible by 2. That's why they're even. And so I'll say, let x be any number or any element 2x so that it's even. But to make this work, then we need numbers that are only less than or equal to 20. So the biggest x can possibly be, if it's multiplied by 2, is 10 now. All right, and then of course we need to have only our counting numbers, so we'll say x is an element of the natural number family. Okay, so there we go. That's in set builder notation. Um, might be helpful again to remind yourself that 2x denotes an even number. It denotes it because any number that's even is divisible by 2. So this set of even numbers is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Every number that I've listed in that set is also part of our universal set. Like we said, all the numbers we're using for these examples are in that universal set. And when one set contains elements that are entirely found in another set, this is referred to as a subset. And in this case, it's a subset of U. Okay, because all of the elements in E are found in U. There's also a nice way that I can write this. I can say that E is a subset of U. I try and make this subset symbol a little bit longer so that I don't accidentally think, oh, that's definitely a C. No, the subset symbol is kind of like a C that you stretched a little bit horizontally. So E is a subset of U. That again means that any of the elements in E are also found in U. And I don't mean that like metaphorically, like the numbers are in your heart. But it kind of sounds weird when I say it that way. Okay, how about O? Let's call O a set of odd numbers that are less than 20. Don't have to include the equal then, because that doesn't make sense. 20 is even. Um, remember, if we have a special way to denote even, we also have one to denote odd. An odd number is always just one more than an even number. So we'll use this, oops, 2x plus 1, such that now if we have x all the way up to 10, we're going to get 21, so that doesn't work. So we have to go x is less than or equal to 9. The other thing we need is if we start at 1, our counting number, then our first number is 3. And that's not the first odd number. So we actually need to include the value 0. And the way we do that is we start with our whole number family, not our natural numbers. Okay, so here's another set. We know that O is also a subset of U. All right, so O subset U. And that's because all of the odd numbers less than 20 are numbers less than 20. So they fall in that universal set of the natural numbers less than 20. Okay, there's another thing that's interesting here. If I take set E and set O and I compared the two of them, I find that none of the elements are shared between them. And so that's one thing. There's another thing as well. If I take set O and set E and I take all of the numbers in both sets, all the elements, those two sets form the universal set, or set U. So we've got two special ideas we're talking about. The first, the fact that they don't share anything, we can say that O and E are disjoint. This means that they don't have any overlap in between their terms or elements. There's no elements in E that are also in O, and vice versa. The other thing that I can say is that if I have a universal set of numbers and O and E perfectly meld to create that universal set with no overlap, I can say that they are complements of each other. So O and E are complements of each other. You're looking great, O. Thank you, E. So are you. Um, that was funny, right? A way I can notate this is to say O is equal to the complement of E. This little like marker here is saying complement of. In other words, taking the universal set, if I take the universal set and I subtract O, I'm left with E. Ooh, ah. Okay, let's do a couple more examples. As you can kind of see, all these examples are very purposeful to show you an idea, right? I don't care that you can count to 20. I really hope you can, I guess. If not, that's some like personal growth you can work on. But what I care about is in all these examples, I'm showing you a specific idea. So if you're watching this and you're taking notes, which you should be if you're in my class, um, don't write a bunch of numbers down. Get the big ideas. Big idea. You need to know, for example, that this is how I say odd. This is how I say even. You need to understand set builder notation. What are the words I'm saying? Pause the video. Go back. When I speak these sentences, I'm telling you what the parts of those, like that notation means. You need to have your terms. What the hell is disjoint? Complements. Oops, sorry. Pardon my French. With these, don't care about the numbers. Care about the ideas. So factors of 20, let's take a look, see at that one. Let's call this group F, F for factors. And what are our factors of 20? Remember, you do need to know what this word means. Factors, those are numbers that have 20 as a multiple. That's another way we can say it. Another way we can say it is 20 is divisible by its factors. So you can divide it by 1, by 2, by 4, by 5, by 10, and by 20. So this is a set of numbers, of elements that are factors of 20. Very nice. Now, are there any sets for which F is a subset? And if there is, we should show it in the right way. Well, F does include some numbers that are less than 20, so we can say that F is a subset of U. But there's odd and even numbers. So F is not a set of either O or E, or not a subset, excuse me, of O or E. Okay, well, how about this? What if I say numbers that are both even and factors of 20? Well, here we can go with, let's go B. I just need a new letter. Your letters sometimes need to kind of make sense, right? F should be for factors, O for odd. But numbers that are even and factors, we name a set with one letter preferentially. And so I'm not going to put EF or FE, okay? I'm going to put B because that's the number that I wrote on my page when I made these notes. All right, so here's my set, even and factors of 20. So that's 2, 4, 10, and 20. This one and the one before, there's not a really good way other than like defining some more ideas to write this in set builder notation. So I'm just going to use roster notation. Okay, let's ask the same question. What sets is B a subset of? Well, because we're talking about a universal set, we know as usual, B is a subset of U. But also B is a subset of F just above. Is a subset of F. And because B is all even, we can say that B is a subset of E. Wow. So this is interesting. The numbers in B are all in F and they're all in E. Okay, that's cool. Interesting idea here is that any number that is shared between F and E is included in this subset B. So this is where B is where F and E, and we'll say this word overlap, because that's not a proper term, but it might help. Like think of a Venn diagram, and we're going to draw a lot of Venn diagrams, so get thinking about them. Our circle for F, which is factors of 20, and our circle for E, if I have those in a Venn diagram, this is where they overlap. And the word we're going to use for that is much better is intersection. Okay, so intersection is going to be our big word. And that word is something that we're going to talk about in like, I don't know, 10 minutes, 5 minutes, hopefully less. This idea, intersection, very important for us. So we'll come back to it. How about numbers that are factors of 20 but not even? This we'll call D, you'll see later why, includes the numbers 1 and 5. Okay, so this is kind of like what's left over. After I take the even factors of 20, my leftover set here is the odd factors of 20, or not even, right? So there's a name we can give this. If I took set F and I subtracted set B, then I would get this set D. And so the word D stands for it's a set difference. Now, I don't think you're going to get tested much on this, but it's a helpful idea of being like, well, let's take these parts out and see what's left over. Yeah, it's a very mathy thing to do. And so, yeah, set difference is probably something you're going to like implicitly, if not explicitly do. One way I could say this is I could say that D is when I take the set F and then I remove all of set, not E, B. B is our even factors of 20. Okay, so D is F subtract B. So again, this is called a set difference. D is all of the elements in the set F that are not also in the set B. Okay, natural numbers that are negative. Well, wait a second. There are no natural numbers that are negative. And so sometimes you're going to have a set like this, set N, which has nothing. And so we call that the empty set. And I can denote it by having a set of empty brackets. This is an empty set. So the empty set here, N, includes nothing, nothing at all. There's another way I can notate this, which is like this. I'm actually going to make sure this looks even prettier. That's not much different, but there you go. So N is the empty set. It includes nothing, okay? There's no natural numbers that are negative. You cannot count to negatives by counting up from 1. There you go. Finally, this isn't exactly in our example, but there's one other idea that we might see a little bit more. Let's say we've got a set like A, which is all natural numbers. So 1, 2, 3, so on and so forth. I can actually denote that a set continues with this ellipsis. Cool. So this set includes all natural numbers, which you could count until your face goes numb. This is what we refer to as an infinite set. It has no end. It includes all numbers, infinite, right? So there you go. All right, so those are a lot of terms that we need to know. There are a couple other big ideas here, but before we do, I'm going to skip a little bit ahead, and I want to highlight a lot of bit ahead that every so often we're going to have these idea checks. And so these idea sets and these idea checks are going to talk about ideas that I've covered in the notes through examples that you need to have written down. There's a little bit extra here and there, but this is a really important set of ideas. All right, going back to where we were. 2 words that are really important are unions or intersections. So I'm going to say these definitions down because they're a little bit longer than I want, and then I'll kind of like paraphrase them, write them down. I just don't want you to waste your life away watching me write on this tablet thing. It's terrible. So the first of these is a union. A union of 2 sets includes all of the elements that are in one or both of the given sets. If an element is in A or B, it is in the union A union B. So here's a kind of a paraphrasing of it. A union is elements in A or B. And when I say or, this can be in A, in B, or in A and B. Okay? So or doesn't mean it has to be one or the other. Or is inclusive. It can include it in both. So if it's in any of these sets or both of these sets, it is in the union of these 2 sets. So a union of A and B, what we use to denote that is this sign. So this is a union symbol. I try and make them a little bit thin because otherwise it looks like a U, which it is. But I want to kind of show off that it is something a little more specific. Okay. So, for example, if I wanted to look at anything, the union of D from before in union with, what was our other one? B. says dub. Like how I'm dubbing this video right now. Anyways, so the union of D and B would actually include all of the elements in set F. If it's in either D or B, it's also going to be in F. That union of the two is our factors of 20. Another word we said before was this idea of an intersection. And an intersection is when an element is in both sets at once, when it's in A and B. So an intersection is A and B. That means it can't just be in one or the other, it has to be in both. It's in that overlap of the Venn diagram, like we were talking about. So, a way we can say this intersection of A and B, we just use this symbol again, but we flip it upside down. Okay. Union is an or. I'm going to box this now. Intersection is an and. Okay. And it's really important to remember that or is inclusive in this context. It doesn't mean it has to be only one or the other. It could be in both. That's an or for you. All right. Let's look at an example here. Let the universal set for this example be all natural numbers less than or equal to 20. There will be two subsets for this example. A, the even numbers, and B, the factors of 20. So using proper notation, let's write out A, B, the union of A and B, and the intersection of A and B. All right, so I'm going to just write it in roster notation so that we can actually see all the numbers. I could try and write this in set builder, particularly like our even number set. We did that already, but I'm going to just write it in roster notation so that you can see everything. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 20. Trying it again. Okay, there we go. B, we're saying is our factors of 20. Okay, so that's 1, 2, 4, 5, 10, and 20. Okay, now we're going to look at the interesting things. What is A union B? Now, one thing that's interesting as well, I said interesting a bunch in that last sentence, so it must be interesting. They actually make their union symbol fatter. Who knows? Maybe over the course of my life, I will change to fatter U's. But I'm not going to body shame you. Okay, anyway, so A in union with B is equal to anything, any element that is in one or the other or both. So if I see a number in either of these two sets, if an element is in one of the sets or both the sets, I include it in their union. So here we go. I've got 1, 2, 4, 5, 6, 8, 10, 12, 14, 16, 18, and 20. Now, there's actually one thing I didn't mention before. The order in which I write these, it seems pretty obvious, right? Because I'm counting. But if I have a set like this, 1, 3, it's equal to this set, 3, 1. Like these are equivalent sets because they have the same elements. The order in which I write them doesn't strictly matter. One thing that, like on a diploma, if you're writing things in a weird order, they might get pissy at you and take marks off. So write it like a normal person might. And then in set builder notation, there are some like phrases in a sentence that if you say them backwards, it's wrong. If you think about set builder notation as writing a sentence using math symbols, just don't mess with it too much. Try and be straightforward, follow the path we always take, and your life is going to be a lot easier from it. Okay, let's change there. Okay, so that's our union of those two sets. Now we're going to make our intersection. And this is, remember, when we have elements that are in both, not one or the other, but both. So A and B both have the element 2, they have the element 4, the element 10, and the element 20. Okay, so Think about this as like a Venn diagram, okay? If I had a Venn diagram, actually, I'm just going to draw the circles. So here are my Venn diagrams. Uh, A is over here. I'm going to draw better Venn diagrams later. B is over here. If I think about the union A and B, that's everything that is in either of these. Whereas if I think about the intersection, that's only the middle here, okay? Man, Venn diagrams are a great way to show off these ideas. I wish we had more practice with them. Well, great news, we do. Here's an example where a Venn diagram might help us display some ideas. So the universal set of animals is given below. That's this list, okay? There are allegedly more animals than this, but jury's out on that. This is the universal set that we're going to use for right now. Arrange these animals into the following sets. M, which is animals that are mammals, and T, animals that walk on two legs. Sketch a Venn diagram to help demonstrate the data and state the sets M, complement of M, M union T, M intersection T, I read those backwards, and the intersection of not M, or M's complement, and not T, T's complement. Ooh, okay. So this is going to take a little bit of work. Before we do that, there's one thing I want to really highlight. In this example, I've bolded two words. These are directing words. And what that means is that they're telling you exactly what they want. The diploma does this. That's why I'm using these words. Not just because I'm needy and I can't trust you to do what I need you to do. It's because the diploma questions for written response will ask you explicitly to do things by definition. So here are the two words that they've given us. First is sketch. Sketch really just means make a drawing to illustrate your point. Your drawing has to have like the proper details to it, right? So you can't just draw a smiley face and say, voila, I sketched you a smiley face, and the smiley face has a speech bubble coming up that tells you your answer, right? You can't just like half try, caught that one, half try making a graph with no axes labels. You'll get dinged for that for sure. So a sketch is like a mathematical drawing that you're making. And that means it follows all the rules that are needed. State, when I ask you to state the sets, that means you're just telling me the answer. You don't need to verify it by doing any sort of algebra or crazy determination. Just say what the answer is. So state is really nice and lovely. Usually on like the smaller questions, 1 mark questions for multiple or written response, sorry, they're more likely to have like a state idea. Or a state can be this an extra little add-on thing at the end of a more complicated question. Okay, so I'm going to start by making my two sets, M and T, sorry. So M is going to be mammals. So let's start our set with the brackets. Squirrel is a mammal. I'm just going to do shorthand for this. On the diploma, you need to write these all out. I just don't want you to have to watch me do this. Chimps are mammals. Humans are mammals. Bears are mammals. I'm going to do full bear. And giraffes are mammals. Okay. Turkeys, chickens, and crocodiles are not mammals. So they are not included in this set. The next set is T. T is equal to anything walks on two legs. So chickens do. Oh no, I need chim and chick because chimp and chicken start with the same letters. Good catch. Humans walk on two legs, and actually so do chimps. So go chim. Now, yes, I know that chimps also walk on their hands sometimes. Sue me. And turkeys. All right, there you go. So we're gonna just say that chimps, for the purpose of this example, are bipedal and they don't use their like knuckles to walk around like monkeys, which they are. Okay, so now let's make a Venn diagram. When I said earlier you need to have proper drawings, this is the proper way that you can draw a Venn diagram. All right. Notice that there is a box, and that box is our universal set. So this we're going to say is U. Okay. Then I have two circles. One will be M and one will be T. Now, I've actually seen where the U is inside our circle and the outside our circle. To my knowledge, this is non-issue, right, between one or the other. But if that changes, I will tell you if you're in my class. And if you're not in my class, go look it up for yourself. Don't be lazy. Okay, now I'm going to put everything that belongs in M in this circle M. Anything that belongs in T in the circle T, and the one that doesn't belong, Crocs, we're just going to put outside of those circles. So notice that I put Croc in my universal set. It's still in this large spot, but it doesn't belong to any of the subsets within, because M and T are both subsets of U. Okay, the other thing to be careful of is there's a couple animals that are in both. So chimps and humans are in both of our two sets. So I'm going to actually start by looking for those two, and I'm going to make sure that they're in our intersection. So I've got chim and hum, or chimp and human. Then I'm going to put squirrels, bears, and giraffes over here. Squirrel, bear, giraffe. And then I've got chickens and turkeys over here. Chickens and turkeys. Okay, so I have all my elements here. One thing that's like a good double check mechanism to make sure you haven't missed anything is count the number of elements in your universal set, which is equal to 8. Remember, there's that notation. I'll just show that off for you. And then count how many things you drew in your Venn diagram. So 1, 2, 3, 4, 5, 6, 7, 8. Good, I haven't missed anything. All right, so now I'm going to just use, actually, I need to remember what I need. So I need the complement of M. I need the union and intersections of M, M, T. And then I need the intersection of the complements of these two. Okay, so now if my Venn diagram is really good, I can use that to just sort of answer out all my other questions. Okay, so the complement of M is anything that is not part of M that would be needed to kind of like fill in the universal set. So that's anything that is outside of, here, let's draw a circle around. Nope, never mind. I'm not going to do that. Anything that's outside of M, but inside of our universal set. All right, and so that is chickens, turkeys, and crocodiles. Those are the missing pieces of the set U that are not included in the subset M. So we'll write that. So here we go. Chicken, turkey, crocodile. There we go. Okay, the union of M and T is all animals that are included in either or M or T. So 1, 2, 3, 4, 5, 6, 7. There are 7 animals. Crocs are the only ones that are not. All right, so let's go ahead. We'll go squirrel, bear. And again, the order doesn't matter. And so I'm just going down the lists here. Chim, hum, chick, tur. Okay. There you go. So there's my set, which is the union of those two. Okay, and then now I've also got my intersection of these two. Intersection is only those that are overlapping. So let's use green. And that's this one, chimp and human. So my intersection between these two is just chimp and human. And then finally, the intersection of our complements. So if I think about like a complement of T, that is anything that's not in T. So that includes crocodiles, squirrels, bears, and giraffes, things that don't walk on 2 legs. However, I also need my complements of M. So that's anything that's not an M. So that's these 3 again. One I need then for an intersection is it has to be in kind of like our notation here, underlined in both yellow and orange. And only crocodiles are part of both of those sets. And so our subset, the intersection of complement M, complement T, is only going to include crocodiles. Okay, cool. So that's a way that we can use Venn diagrams in order to demonstrate ideas about sets. But there's actually a lot more we can do with Venn diagrams, including some really nifty math. Okay, so Venn diagram for students. Here we go. We've got people going to Castle Mountain, which is a ski resort, in case you don't know. Of this group, 29 of the students can ski, 20 of the students can snowboard, and 6 of them do neither. Why are they going? Maybe they're like telemarketers? Okay, sketch a Venn diagram illustrating the situation and determine the amount of students who ski and snowboard. Okay, sketch means draw a mathematical diagram. Determine means provide supporting evidence towards a conclusion by using mathematical techniques. And I'm paraphrasing these, but that's sufficiently accurate. If you ever want to look this up, all of these definitions, these words, guiding words, are found in the Math 30-2 bulletin. So they're there for you. So when I say determine, I need like a proof of what I'm doing. And this brings us to our newest tool in the toolbox, which is called the principal. Is it LE? No, principal. I think it is LE. On my notes, I have it like a principal, like of a school. How funny. So the principle of inclusion and exclusion. Okay. And this principle we're going to see a couple times. We're going to start by seeing it in its simplest form when we have two sets that have an intersection. And what this tells me is that if I want to know the number of students that are in either or, is going to be equal to all of the students in A plus all of the students in B. But if I do that, if I count all the students in A, all the students in B, what I find is that I'm going to double count some of the students. What if a student is in the union in A and B? Well, then I need to go ahead and I need to get rid of that double count. So I count students twice if they're in the overlap and the intersection. So I need to get rid of one case of that overlap. Wow, nice B there. So the number of elements in the union of A and B is equal to the number of elements in A plus the number of elements in B, subtract the number of elements in the intersection of A and B. Interesting. Okay, so we can do our math now, and then we'll fill in the Venn diagram later. One thing that's nice to note is even though it says sketch first and determine second, we don't have to do it in that order. We have to do those two jobs. The order in which we do them is determined by what's easiest for us. But like a marker on the diploma is their job is literally to make sure that they look at everything you do. And if you do things the right way, even if it's out of order, you'll usually get the marks. Okay, so how many students are in A or B? Well, there's 47 total students, but 6 of them do neither. So that means we have 41 students in that group. 29 of them can ski. So let's call group A is ski and group B is board. Okay, so group A has 29 elements. Group B has 20. And then this is what we're looking for. And so I'm going to use a variable X to denote A union B. Okay. Nice to keep kind of like a legend going for anyone marking. They don't have to guess what I'm doing. All right. Now this is why it's called a determined, because now I've used a math principle and now I'm going to use algebra to solve this out. So I'm going to isolate my variable X. I'll do that by taking 41 and I'll subtract 49. So I get -8 is equal to -x. Okay. And if you need to take more time on your algebra to make sure you're isolating it right, go for it. If you added the x over and then subtracted 41, go for it. I don't care. Do algebra. You're not in grade 5 anymore. Okay, then I'll divide both sides by -1 to get this. X is equal to 8. So I can say, therefore, 8 students board and ski. Sweet. So now I've got my numbers. I'm going to make my Venn diagram. oops, drawing dots everywhere. So I'll start with my box for the universal set. I'm going to make my two ovals. They don't have to be perfect circles. You're not getting marked on cleanliness, just accuracy. So this is going to be U, A, and B. And now in this case, I don't know who the students are. I'm not writing like chimp and turkey and human. I'm just going to put how many people there are in each. So we said that there are 6 people who do neither. So they're outside of our 2 subsets. They're in our universal group outside of it. There are 8 students who do both. Now, the last piece here is that if I know 29 students are skiers, 8 of them can also board. I don't want to put 29 here again. I'm double counting. That's the whole problem. So if 8 of them do both, that means only 21 are only skiing. If 20 do snowboarding, 8 do both, that means 12 of them only snowboard. Now, remember our sum, our universal set, and U was equal to 47. So when I count these all up, it should equal 47. 8 and 12 is 20, 41, plus 6 is 47, so that's good. Okay, there we go. So there's our Venn diagram. And I really like using the principle of inclusion and exclusion for finding this. But finding this, like this number, sorry, and 12, it's really easy when I see it in the Venn diagram. All right, so those are Venn diagrams. We're going to see a couple more examples. One we're going to make, another we're going to, no, I lied. 2 more we're going to make. One we're going to see as a like a diploma question where they made it and we have to use our math. Okay, so a high school survey asked 50 students about their favorite sports. The results showed the following. How many students liked at least one of these 3 sports listed? How many students only liked one of them? Okay, so this one, they give us a lot of information, and it's going to be a little bit easier if we start from the middle and work outwards. All right, so let's go ahead and let's fill this in. So here's our box. Now remember, there are 3 options here. We've got the set volleyball, which I'll call V, S, and B for basketball there. So I need 3 circles here. I'm not super worried about their sizing because I'm just writing a number in there. Okay, and then I have my universal set. Remember, when they say we asked 50 students, that doesn't mean 50 students picked these. That means that's our universal set, not the total number inside the circles. So I've got BSV. Okay, and let's start with our center. Remember how I said I love working from the inside out? 3 students liked all 3 sports. So that tells us this. Only 3 kids are in that middle intersection. All right. Then we'll go kind of up the line here. So I'm actually working backwards through this. 10 students liked soccer and volleyball. And that could include this group of 3 here, right? That liked soccer and volleyball and basketball. So if there are 10 that are in this intersection between, and I'm just going to shade this for a second. There's 10 in this intersection between soccer and volleyball. We're already counting 3 of them in that overall intersection between all 3 groups. So that means there's only 7 left right here. 7 students like basketball and volleyball. Again, 3 to get to 7, we need 4 to be here. And 8 students like basketball and soccer. So that's 3 plus 5 would give us 8. All right, awesome. So we've got that there. Now let's look at our individual cases. So if 15 people liked volleyball, and we have 3 plus 7 is 10, 14, that means only 1 person only liked volleyball. For soccer, 22, that's 15 is in our little intersection sections. Oh, that includes soccer. So we have 7 students left. And if 18 kids like basketball, that's 12 here. So we have another 6 that are not included. Okay, so this looks like it's almost all filled in, but we're missing one thing, and that's our universal set. Remember, we asked 50 kids, so let's see how many are in these groups, and anyone that's not in these groups, we'll have to include here. So I'm just looking for groups of 10, so that's 10, 20, 32, 33 kids are in this group. So if we had 50 total, that means 17 kids are excluded from this set of sports. Maybe they all like ping pong or something, or football, or I don't know. There's lots of sports. You pick your favorite. Field hockey, thumb twiddling. Anyways, this is now a completed Venn diagram. If you missed this, you would lose marks because it's part of the diagram. So make sure you're careful in that. Now, let's look at our questions. How many students liked at least one of these three sports listed? Well, that means that the number of people that are in this intersection, no, sorry, union, A is not one of our groups, B or S, we said that's 33 students. So who is included in at least one of these circles is 33 students. And then how many students liked only one of these sports? This one's a little bit harder to notate, so I'm just going to write my answer. Only one is equal to 7 plus 7 is 14 kids. Okay. And then if I was on the diploma, I would probably write these also as a sentence and say, there are 33 kids that like at least one sport. There is 14 kids that like only one sport. One thing that you might see here, I did not include those guiding words. You might see something like determine or sketch again. All right, here's a past diploma question. This is a multiple choice question, obviously. And so you'll see a lot of these Venn diagrams in multiple choice questions, not just in creating them, okay? Okay, so a particular junior high school offers cooking drama and computer courses as options. Students at the school were surveyed to determine which options they are enrolled in. The Venn diagram below represents the data that were collected. Isn't that nice? Data is a plural. So you don't collect a data, you collect data plural. So that word, thank you diploma writers for that one. So the number of students enrolled in cooking or drama, but not computers, is what? So let's go ahead and let's put some blue on what could work, and then we'll cross out what can't work. In cooking or drama, that's inclusive. That means anything that's in cooking or drama gets underlined. So it can be in the intersection, or it can be just alone, cooking or drama. Oh, look, there's you on the outside. So maybe we'll start putting you on the outside of our things. All right. Then not computers means anything that is computers gets crossed out. All right. Got rid of it. So that narrows us down a little bit. Now we've got 42, 15, and 23. These three numbers we can add together to get our sum. So that's 57 plus 3 is 60 plus 20 is 80 is our answer. There are 80 students that are in those criteria. I would say that this multiple choice question isn't too hard, but it highlights something very nice. And that highlight is a Venn diagram is really good at visualizing an abstract idea of these intersections and concepts. So when you're looking at all these things and you're thinking, how do I do this? Think about it in terms of a Venn diagram. All right, I got one more question in this half of the unit, and then we have three little fun practice problems for logic puzzles. Here's a new one. In a survey of 100 people, it was found that a lot of them like different things. There you go. How many people like all three fruits? So they tell us about a lot of the intersections, but not the big one in the middle. And so one we need to use again is our principle of inclusion and exclusion. Inclusion plus exclusion. Okay, so our principle of inclusion and exclusion, now that we have three options, so we're going to have to tweak it a little bit. Here's how it's going to look. The number of elements in apples or oranges or bananas is equal to, again, our number in apples plus our number in bananas plus our number in oranges. Doesn't really matter that I changed the order. Don't freak out. Then I want to get rid of those those overlaps, right? So we have the overlap, the intersection of A, where am I? And B, overlap of B and O, and the overlap of A and O. There you go, just trying to remember which one I missed. So this gets rid of all of our overlaps, but you might be thinking, wait a second, if I get rid of every single overlap, I'm getting rid of the area in the middle one too many times. I've cut out overlaps over and over and over again. If I constantly am cutting them out, that whole area is gone. And so the people that are in there are missing. So what we actually need to do is we need to add back in N of A and B and O. Okay, so this actually now gives us what we need to solve for this because we actually have all the other pieces. All right, another thing to expect, the guiding word for this question would be determine. Determine how many people liked all three fruits. So how many people, if we surveyed 115, didn't like any of them, that means we have 85 people who are in this overall union. Number of people who liked apples was 60. Number of people who liked bananas was 45. Oranges was 55. Subtract apples and bananas was 30. 25 oranges and bananas. And then apples and oranges was 35. There we go. Plus, and I'm just going to call this X. That's a 2. Let's try again. X. Okay, and there we go. Okay, then I'm going to pull out a calculator. I'll add all these numbers together. I get that 85 is equal to 70 plus X. So to isolate X, I subtract 70 from both sides, and I find this. 15 is equal to X. Excellent. All right, so I've got this. X is equal to 15. So 15 people liked all three fruits. Now, another thing they might ask is they might ask us to do a Venn diagram of this. So I'll go ahead and I'll do one now just so that we've got it. Go ahead. 1, 2, 3. Okay. And like we said before, I'm going to put U on the outside. Okay. And we said that 15 people like none of them. This is O, A, B. All right. So we did our math. We calculated that 15 people liked all of them. So that'll go in the middle. Then we can kind of go through our list. So people who liked apples and oranges is 35. 15 are already included here, so we have 20 more here. 30 people liked apples and bananas, so that means there's 15 left over here. And then, of course, if 25 people liked oranges and bananas, that's 10 more here. All right. People who only liked oranges then, well, that is going to be 10 left over here. Only liked bananas is 5 left over here. And only liked apples is another 10 over here. Okay, so there we go. I did these last steps of math a little quicker, but that's because we kind of see the pattern. I'm just going to get you through this video. What's the last thing I need to do to make sure I haven't screwed this up? I better make sure that I can actually like count out all my numbers and see that they add to 100, because that's how many people were surveyed. So I have 15, 30, 45, 65, 70, 80, 90, 100. However you want to add that up, I like just looking for nice groups. I did get 100, so I know this Venn diagram is delicious, nutritious, and correct. Awesome. So that's essentially everything we're doing. If you want some hints on what you should really practice, Venn diagrams, obviously, notation, what do all these symbols mean? Like that first example we looked at, and using the principle of inclusion and exclusion. I've shown you the two basic forms of it when we have 2 overlaps and when we have 3 overlaps, but you really, really need to practice it to master it because you're going to get asked questions about it, all right? The next half of this unit, puzzles, let's just look at some of the examples we have here because it's nice to see questions that have been asked in the past and ways of solving them. And then you'll realize that there's kind of one theme, and that's that you don't have to know anything. You just have to think about questions. You are expected to use logical processes, but you're not expected to memorize any rules. So it's not important for you to memorize how to play Sudoku. You do need to know how to apply the rules of Sudoku. Here's our first kind of puzzle. In a particular game, drawings consist of circles or squares. Different letters are used to describe the type of shape, the number of shapes, and the arrangement of the shapes in the drawing. 5 drawings from a particular game are shown below. And there you go. So based on the drawings above, which of the following statements about the letter A is true? When we're given a question like this, we might want to think about our work from 20-2 where we thought about like counter examples. If I know only one thing can be true, that means the other 3 must be false. And that means I should be able to disprove them by counterexample. So let's find a counterexample for each of these. All right, the letter A represents circles. Well, my counterexample is that one. These are squares. If A meant circles, Abe should have circles. All right, the letter A represents squares. This one is also going to be easy. I'll do a different color just to show you. Ace has circles. If A represented squares, Ace should have squares. The letter A represents overlapping shapes. Ooh, well, all of those do overlap, but let's make sure we can do a counterexample for D first. The letter A represents the number of shapes in the drawing. Well, these 2 have different numbers, so it can't be that. So yeah, that means our answer must be C. Notice we're going through, I'm not just proving by using like logic here. I'm actually more focused on disproving by using logic to make those easier. Now, one thing that's more common though for logic is that they'll put it in a numeric response question. So you actually have to kind of do a little more thinking. You can't just use simple logic to dismiss things. The puzzle below requires the player to fill in the squares with the digits 1 through 9 inclusive. So it includes 1 or 9. So that the digits add up to the numbers shown in the triangles. For example, in the second column, the entries are 8 and 5. Oh, that gives you 13. Excuse me, I'm having so much fun. Find out what each of these is. So we'll just walk through them. So if this column here has to have a sum of 9, and our other 2 numbers are 6 and 2, our missing number must be 1. Yep, that's it. That's all we're doing. Right, how about B? Well, 17 is this column. Okay, so our missing number is adding to 17. We've got 4 and 8 plus B. Well, 4 plus 8 is 12 plus 5 must be our missing number. Yeah, I know. Tough stuff so far. Okay, C. Well, C, it might be easiest to go this way because we don't know D, so you can't go here. Or maybe you could solve D first. Look, there's 1,000 different ways to skin this metaphorical cat. If I add all my numbers together, I get 11, 19, 26, 27, 29. What more do I need to get to 32? I need 3 more. Okay. And finally, if this is 3, and I need to add something to get to 4, that means D must be 1. Like, honestly, I have not seen a lot of diploma questions on logic that are what I'd say is difficult. The next one, I guess, is the hardest I've seen. So you'll see that. But this kind of opens up an idea for you, hopefully, that if you're doing the diploma in June or January or whatever J month you choose, and you are strategizing how best to write that test, maybe you hunt down some of these logic problem questions first because they're a good confidence boost. They get your mind working, right? You don't have to have memorized a bunch of different rules to solve them. And they're pretty darn easy, right? So look for some easy things to start your test. Build that confidence. Last one, like I said, it is the hardest. In a particular puzzle, the digits 1 through 9 are placed in 9 circles arranged in a triangle. Each digit can be used only once. When the puzzle is completed, the digits on each side of the triangle must add to 17. A partially completed puzzle is shown below. This is, like I said, a harder one. And so in the ones before, we had a very obvious and clear strategy of how are we going to do this? This one, I'm going to show you the strategy that works best, but it's tough. And so if you run into a question like this, or maybe it's in another unit and you say, I don't know how to attack this in an effective way, skip it and come back. The nice thing about all these logic puzzles is that there's like a finite number of ways you can do this, and you just screw around with it until it works. That takes time though, so don't do that on your first run through of the questions. All right, I'm going to write out all the numbers first. So 1 through 9 inclusive. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm going to cross out the ones that are already in the puzzle. So 2 is there, 5 is there, 6 is there, and 9 is there. So I have 1, 2, 3, 4, 5 letters or numbers for 1, 2, 3, 4, 5 letters. Okay, so that adds up. Then I'm going to write some math statements to help me out. So I know that all of these edges, these sides, are going to add up to be 17. So I have A plus 6 plus E plus 2 equals 17. So I'm going to say A plus E plus 8 equals 17. That means A plus E must equal 9. Okay, that's helpful. Then I have this line here. So I have 2 plus 5 plus D plus C equals 17. And this tells me that D plus C must equal 10. Okay, and the last line I know is that if these all add together, that means A plus B plus C must equal to 8. And that's because 17 minus 9 is 8. All right, now this is nice. This is a good kind of deductive reasoning business here we've got, but it still might not be very clear how we can make this work. And that's okay. Skip this question and come back. But here's a nice thing. If I look at A plus E equals 9, and I look at these numbers, there's only one combo that'll actually work for us. And that's that 1 and 9 is, or 1 and 8 is equal to 9. So we can say A and E equals 1 and 8. Okay? So we know A and E is 1 and 8. D and C, likewise, there's only one combo that adds to 10 that's of the letters left. That's D and C are equal to 3 and 7. And finally, if I look down here, I know that if I take the high number in either of these, it won't add up to 8 with C left over. I know C has to be 4 because that's the only number that's not listed here. So C is 4, and I'm going to write on this. You can write all over the diploma. You should write all over the diploma. It's eerie looking through diplomas and you scan through it and they have nothing written there because they're psychos or something. I don't know. It makes you assume that they did the stuff wrong. So write all over the diploma. Use it. It's yours. Okay, C is 4. That means A is the low number of these. So A must be 1. And B is the low number of... Oh, no, C is not 4. Hold on. B is 4. Good catch, me. C is this one. I thought this was a B at first. So, all right, so B is 4. That means C is the low number. C is 3. Okay. If C is 3, that means that D is 10. Not 10, 7. And if A is 1, that means E is 8. Okay, then I'll go through and I'll verify. 1 plus 6 is 7, plus 5 is 15, plus 2 is 17. Good. 2 plus 5 is 7, plus 7 is 14, plus 3 is 17. Good. 1 plus 9 is 10, plus 7 is, yeah, okay. So all of it works out. This works. Woohoo! I have only the numbers 1 through 9. No repeats. We're golden. Okay, so B is 4, D is 7, and E is 8. So that's my answer. Woohoo! Look, we're done. We're done. I don't know how long I've been talking for, but it feels like roughly one eternity. Hopefully you find this video helpful. If you watch this whole thing straight, you're an idiot. No offense, but you should have paused it partway through and took notes and did practice. And if I am talking to you and calling you an idiot, sorry, that was rude. But next video, don't watch the whole thing in a row. That's just psychopathic. Do practice. This is, again, not sufficient as your only resource for going through this. You will not find success if that's the only thing you do. You must practice. Okay. Best place to practice, whatever your teacher tells you to do. Alternatives, Quest A Plus has a lot of stuff, and old diploma items, that's just perfect. Do those.